Hello everyone, this is Mrinal Kanti Roy Chaudhary. The title of the talk is Some Discussions on the Definitions of Quantization Error and Quantization Dimension. So let me first tell you what is the constraint quantization error. Let P be a Borel probability measure on RK equipped with a metric D induced by a norm this on RK. And let R be a positive real number. And Sj be a family of closed sets with S1 non-empty. Then for any positive integer n, the nth constrained quantization error for P of order R with respect to the family of closed sets, this Sj, is defined as follows. So VNR equal to VNR P equal to this. And you see that the set alpha is coming in the case of nth constrained quantization error from the union of Sj, j is from 1 to n, and cardinal alpha lies between 1 to n. Now, unconstrained quantization error which is traditionally known as quantization error, is a special case of constrained quantization error. So if you put all Sj equal to Rk, then the definition of nth constrained quantization error reduces to the definition of nth unconstrained quantization error for P of order R, which is given as follows. B and Rp equal this. See that here all Sj equal to Rk, so alpha becomes the subset of Rk now. Here also cardinal alpha lies between 1 and n. Remember, it is nth quantization error, but you are writing cardinal alpha lies between 1 and n. A common question. In the definition of nth quantization errors, both in constrained and unconstrained scenarios, instead of saying cardinality of alpha equal to n, why it is written cardinal alpha lies between 1 and n? Here is the answer. Let me first give you the explanation in the unconstrained scenario. Write Vp alpha, which is this distortion error. Now, if the support of P contains infinitely many elements, then infimum Vp alpha, alpha is subset of Rk, cardinal alpha equal to n is same as cardinal alpha lying between 1 and n. That is, if the support of P contains infinitely many elements, then V and Rp is strictly decreasing. If the support of P contains finitely many elements, say capital N elements, then for any positive integer n less than equal to capital N, we have cardinal alpha equal to n is same as infimum Vp alpha, where cardinal alpha lying between 1 and n. That is, V and Rp is strictly decreasing for positive integer n lying between 1 and capital N. And if the positive integer small n is greater than equal to capital N, then you see 0 equal to infimum. This expression is equal to 0. Infimum Vp alpha, always subset of Rk, cardinal alpha equal to n. And n is bigger than equal to capital N, where capital N is the support, number of elements in the support. And this expression is equal to this same. This expression says that V small n comma Rp equal to V of capital N comma Rp equal to 0 for all small n greater than equal to capital N. Now look at the three cases. Right hand sides are same for all the three cases. Because of the above reasoning, to give a unified definition in the unconstrained scenario, in the definition, we write 1 less than equal to cardinal alpha less than equal to n. Let me now explain why this is happening also in constrained scenario. Here it is. Write Vp alpha, which is the distortion error. If for each positive integer n, there exists at least n elements in the union, j equal to 1 to n is j. This is the term that occurs in the definition of nth constraint quantization error, that is this one, this union. If this union contains at least n elements, the interior of the Voronoi regions of which have positive probability, then cardinal alpha equal to n is same as 1 less than equal to cardinal alpha less than equal to n. There is distortion in view of these two expressions are same. That is, in this case, V and RP is strictly decreasing. Now, if the union j equal to 1 to n is j contains finitely many elements, say capital N elements, the interior of the Voronoi regions of which have positive probability, then for any positive integer small n less than equal to capital N, we have this infimum when cardinal alpha equal to small n is equal to same as this infimum when cardinative alpha lying between 1 and n. Now, that's b n comma rb is still decreasing for this in this case. Now, if small positive integer is greater than equal to capital N, then this expression, of course, non-negative, is equal to same as 1 cardinal alpha less than equal to n. That is v n comma rp equal to v n rb for all small and greater than equal to capital N. Because of the above reasoning, to give a unified definition in the constraint scenario, we write in the definition of nth constraint condition error 1 less than equal to cardinal alpha less than equal to n. Okay, now constraint quantization dimension. Let V and RP be strictly decreasing sequence and write V infinity R equal to this. And write D lower bar R equal to this expression and D upper bar R equal to this expression. These two expressions are called the lower and the upper constraint quantization dimension of the probability measure P of order R respectively. If these two expressions are same, then we call it the constraint quantization dimension of P of order R. In the unconstrained scenario, this term V infinity comma RP is, this limit is 0. So this definition reduces to the definition of quantization dimension in the case of unconstrained scenario. So here are the two expressions, and these two expressions are called the lower and the upper unconstrained quantization dimensions of the probability measure P of order R respectively. And if these two expressions are same, then we call it the unconstrained quantization dimension of P of order R. Traditionally, in the literature, it is known as the quantization dimension of P of order R. Now, there is a question, a common question. Is the quantization dimension defined for all Borel probability measures P? Answer. In the constraint scenario, the lower and upper quantization dimensions of a Borel probability measure is defined if the support of P contains infinitely many elements and the union this contains at least n elements for each n belongs to n positive integer, for each positive integer small n, the interior of the Voronoi regions of which have positive probability. Otherwise, the quantization dimension is not defined. In the unconstrained scenario, the lower and the upper quantization dimensions of a Borel probability measure is defined if the support of P contains infinitely many elements. Otherwise, the quantization dimension is not defined. From the above two items, we can easily conclude that the quantization dimension in both constrained and unconstrained scenarios of a Borel probability measure with finite support is not defined. Though sometimes it is called that the quantization dimension of a Borel probability measure with finite support is 0. Of course, if you consider log 0 equal to negative infinity and k over infinity equal to 0 for any real number k, then the quantization dimension equal to 0 comes from the definition of quantization dimension that is described here. Now the references, these are the two good sources to know all the reasonings. Constant quantization for probability distributions, another is constant quantization for the Cantor distributions. If you have any question, please email me or make some comments. Thank you.